Hello everyone, I am Joaquim Brugués again, and today I'm presenting the solution to an exercise of your list of problems. This is exercise number 12 on your list of symplectic geometry. So you can see here the same statement as in the list. So this problem deals about integrable systems, and in this case in the spherical pendulum. So here we don't see the modeling of the problem, but just in case, if you are not familiar with the spherical pendulum, it consists on a mass that's hanging from a rod that has negligible mass and cannot be extended nor shortened, so it's a rigid rod. So in the case of the simple pendulum, this is allowed to swing in the plane. So this is the logical generalization in which our mass is allowed to hang around, to swing in the whole three-dimensional space. Of course, the movement is restricted to 2 dimensions instead of the 3 dimensions of the space, because it's attached to this inextensible rod. So the movement in practice takes place inside of a sphere. So the way we have chosen to study the problem in the sphere is using spherical coordinates. So these are theta and phi. So just to make clear what these coordinates are, I have down here a picture. So the angular coordinate phi is the angular coordinate in the plane, right, as in 2 dimensions, and phi is the angular coordinate that kind of follows the z coordinate in R3. This has to do with the fact that the pendulum, the only force acting on the pendulum that we are taking into account is the gravity. So this theta will be the coordinate that accounts for that energy in this case. Each of these angular coordinates has a momentum associated with it. So these are denoted by this chi sub theta and chi sub phi. These are the momenta associated with these coordinates. So given these coordinates, we have this expression for the energy. This part is the kinetic energy, and this part, the cosinus of theta, is the potential energy due to the gravity itself. And yeah, as you can see, this is taken without constants, like completely adimensionalized. We are not taking into account the constant of gravity, nor the length of the rod, or the mass. Everything is assumed to just be 1 to make things easy here, because we are just interested in the configuration of the system. So the goal of this problem is to prove that this is an integrable system in the symplectic manifold cotangent bundle of the sphere with the Liouville symplectic form. So just to make things clear, the Liouville symplectic form has this expression here, where each space coordinate is paired with its associated momentum. So I thought that it would be good to have a quick recap on the theory that it's relevant to this problem. So I've just prepared this. So just to recall, we have a really tight relationship between classical Hamiltonian mechanics and symplectic geometry, and this appears in this context here. So in classical Hamiltonian mechanics, when we are given the energy, we deduce the system of ODEs that governs the movement of our particles. So what we have is that we compute the partial derivatives of the Hamiltonian with respect to the momenta and with respect to the spatial coordinates, and the system of ODEs takes this system where each position is related to the partial derivative with respect to the associated momenta, and the momenta with respect to the partial derivatives with respect to the position with a minus sign. The thing is that this system of equations can be readily generalized to manifolds by means of symplectic geometry, and the construction that we do is what I usually call symplectic gradient, although this notation is not universal, but it has the same principle as the gradient in Riemannian geometry, where we are given a function, and from this function we get a vector field. So I think this has a very similar idea, and the symplectic gradient is the only vector field, the unique vector field that is given by this expression here. Here this minus sign does not appear in all the sources. It depends on the source that one is using. We use it for a couple of reasons. The one that makes more sense here is the fact that if we replace everything with the standard symplectic manifold R2n with the standard symplectic form, then this expression will yield this system of ODE. So we will recover the classical system from this more compact formulation. Of course, if we don't have this minus sign, then we just have the opposite. So this system is not that different. Geometrically we have the exact same information, but we think it's nice to have exactly coincidence here. So the goal of the problem is to prove that this is an integrable system. So I will recall the definition of integrable system. So given a symplectic manifold, an integrable system is a collection of functions where the number of functions is the same as half the dimension of your symplectic manifold, and we ask for some precise conditions on these functions. First of all, we need them to commute one respect to the other with the Poisson brackets, and then we are asking for this condition which is sometimes called generic independence or functional independence, which I think it's not so different to asking for these functions to be linearly independent as vector fields, to say so, almost everywhere. And this Poisson bracket, I assume that you are already familiar with this, but we'll recall here the expression for this Poisson bracket in the context of symplectic geometry, and this consists in pairing the symplectic gradients of the given functions f and g using the symplectic form. The nice thing is that if we substitute the expression of this the definition of the symplectic gradient of f in this case in this expression, we get this where the dot is the pairing of a one form with a vector field, and if we replace this by the definition of the differential function, we see that the Poisson bracket is describing how the quantity f changes along the integral curves of the symplectic gradient of g. Or if we turn things around here and we replace the same formulas, here we have how the quantity g changes according to the integral curves of x sub f. So that gives a good intuition of what this bracket is giving us. So the fact that the bracket is 0 is telling us that each quantity does not change along the integral curves of the other symplectic gradients. And here I said that in most Hamiltonian systems one function is already given by Hamiltonian. I say most here because at least we need to ask for our Hamiltonian to be satisfied that its differential does not vanish almost everywhere, because of course otherwise this condition is not satisfied. In our case, for instance, it is like that. So in our particular case, our symplectic manifold is the cotangent bundle to the sphere, so n is equal to 2, and we already have one integral of motion. These functions sometimes are called integrals of motion or first integrals. So f1 is already given by the energy here, right, by this function. So actually the problem is only asking us to find a second integral of motion. So perhaps just by looking at this expression and by looking at the problem, one is already able to deduce what this integral of motion should be. But for my part, I think that the best way to have an intuition of what we should do here is just starting to compute. So just taking this energy and compute its symplectic gradient. So using this formula here, I already did this computation here. So in order to compute the symplectic gradient, what I usually do is to first write a generic expression for how the symplectic gradient should look like. So we have this u sub t sub phi, u sub t sub theta, u sub phi, u sub theta, and I plug this generic expression inside of the symplectic structure, the Liouville symplectic form that I already gave you before. So after plugging that in, I get this one form. Now I compute the other side of the equation, the minus differential of my energy, and I get this expression. This is the heavy computation part of the exercise. But after computing that, you can just start pairing things and you get the expression of your symplectic gradient. So of course the part that accompanies differential of t sub phi is this part here, so it appears here, and so on and so forth. It's important to note that here in this differential we have nothing with d sub phi, so u sub t sub phi is equal to 0. So here we have the expression. Perhaps at this point it is clear for you what the integral of motion should be, but I think it's even clearer if we take this vector field and write the equations for the flow of this, for the integral lines of this vector field, or saying it another way, the classical Hamiltonian formulation of the problem. So if we just replace it here, it's quite clear now that we have this system of ODEs, and here we have a very suspicious equation, right? We have that the derivative of the moment associated to phi is equal to 0. So perhaps this is exactly the integral of motion that we are looking for, and this is the candidate we are looking for here. Before proving that this is actually the integral that we want, let me just go back to the picture here and try to argue why this makes a lot of sense from a physical point of view. So if you imagine that the pendulum is fixed here at the center of the sphere, so the particle is swinging around in this sphere. It's important to note that the only force that's pulling our pendulum is the one of the gravity. So in a way it makes a lot of sense that the momentum that is orthogonal to this to the gravity, to the force of gravity, which is the momentum associated to phi, that should be constant. That makes a lot of sense. There is no acceleration in that direction. So that's my way to think from a geometrical point of view or from a physical point of view. Why should that moment be constant? So this is our hypothesis. The first integral for this system is c sub phi, Perhaps you consider that this is already proven. I will just really compute this, although the proof is already there. So we need to check that the Poisson bracket of the energy and this moment map is equal to 0, and also that they are generically independent. So here I have the whole computation. Sorry. So I will just walk you through this. So if we compute the Poisson bracket here of the energy and the moment, the angular moment associated to phi, we can just substitute here the expression, and we can use the formulas that I already gave you in a previous slide that I spent so much time on, and here we have this expression. We can just replace the whole expression of the symplectic gradient of the energy here. We have this whole monster, but it is important to note that this dot is a pairing, right? It's a pairing between one forms and vector fields. So we can think that this is just a vector on a basis, actually, and its dual does not appear here anywhere. We don't have the partial with respect to chi sub phi. Therefore, this pairing must be 0. So this is actually 0 as we will expect. Of course, we could say that just because this expression here, we already know this involutivity, because the idea is that the momentum associated to phi, this planar angular momentum, does not vary as we go through the integral curves of the solution of this system, right? And that is precisely the idea of the involutivity, as I explained before. So we can consider that this is proof enough, but here you have the whole full-fledged computation. And on the other hand, we need to check that these two functions are generically independent. So we need to compute the differential of the energy, but we already did this here. Of course, the sign is the opposite, but we just take the opposite of this, and that's it. And we need to compute the wedge product with respect to the differential of chi sub phi. So this component here vanishes, and we are just adding that component in these two summands, and therefore we have this expression here. Now, if we compute the points at which this vanishes, we end up with the conclusion that the only points where that happens are the when the momenta are equal to 0 and theta is equal either to 0 or to pi. So if we go back to the picture here with the pendulum and so on and so forth, those points are only the north pole and the south pole. So in the configuration space there are only 2 points, and going up to the phase space, considering the momenta, we are asking for the momenta to be 0, so these are actually only 2 points in the cotangent bundle of this sphere. And they do coincide with the critical points of the energy here, so that's a nice coincidence. This does not always need to happen, but it's a nice coincidence here. But in particular, there are only 2 points inside of the whole cotangent bundle, therefore it's a set of measure 0. So this this expression is non-vanishing almost everywhere. So this is it. This is the proof that this is an integrable system. And perhaps the exercise could be concluded here already, but I wanted to give an insight of why this, of why having an integral of motion is kind of relevant for these systems. So I had this slide where I just take this a step further. So if we take the momentum associated to phi, we impose this to be constant. Well, we did this, that is constant. Then we can try to apply this to this whole equations. So we need to take into account that every time that this momentum appears, this is a constant. So here this is a constant, and here this is a constant. And we can see that these two equations are actually one second order ODE, or we can leave it as two first order ODEs. Either way is valid. And we can see that this equation here actually plays no role in the system. So what I mean by this is that this second order ODE is extremely complicated. Of course, it does not have an analytical solution, but if we somehow retrieve a solution from here at theta, we can plug it here and we have an immediate solution equation. We don't need to do anything here. We can just integrate and we get the solution for phi. Therefore we go from a system of 4 ODEs to a system of 2 ODEs, or an ODE of order 2 plus an integral. So this can be seen as a system of 3 ODEs, but it's actually greatly simplified. So this is the way in which having integrals of motion, in which having the symmetries helps you, right? You're allowed to reduce the order of complexity of your system. And here we have not even started looking to the to the energy, because the energy may help us to even reduce further the complexity of this system. But I think this is a nice addendum to wrap up what can be seen in this kind of problems. So I hope that this solution was useful for you. Please contact me in any way if you have questions, and I hope that you are taking care. Bye.